In this video, we will discuss about moments of Weibull distribution. Moments, Weibull distribution. So moments we denoted as mu r dash about any value, row moments. So this can be written as expectation of x raised to the power r. So here uh, Weibull distribution is continuous probability distribution. So for we are going to calculate the moments. So we take the limits as integral 0 to infinity x raised to the power r into fx dx. So this we can obtain as integral 0 to infinity x raised to the power r and fx. So fx we write down the PDF of Weibull distribution. So beta upon eta into x upon eta raised to the power beta minus 1 into e raised to the power minus x upon eta raised to the power beta into dx. So here we take as beta upon eta outside from the integration. So this can be written as x raised to the power r into x upon eta raised to the power beta minus 1 into e raised to the power minus x upon eta raised to the power beta into dx. So again, when we are going to solve this integration, so we use the substitution. So now we let x upon eta raised to the power beta is equal to y. So now we can write down as x upon eta is equal to y raised to the power 1 upon beta. So this x is equal to eta y into 1 upon beta. So what is the value of dx? So when we differentiate this, so this gives us 1 upon beta y raised to the power 1 upon beta minus 1 into dy. So now when we talk about the limits, so here for lower limit, so for lower limits, so we have the limit for x as 0. So that means when x is equal to 0, so when x is equal to 0, so this gives us y equal to 0. So that when we put x equal to 0, so 0 upon eta raised to the power beta. So that means y equal to 0. For upper limit, so when we are going to obtain upper limit, so upper limit we have x is equal to infinity. So this gives us so infinity upon eta raised to the power beta is equal to y. So infinity upon something means infinity or power infinity then infinity. So this gives us infinity. So we have the limits, lower limit is 0 and upper limit is infinity. So these are the limits for y. So now we change the integration in y. So now we write down this as this is equal to beta upon eta integration 0 to infinity. So what is the value of x? X value is eta y raised to the power 1 upon beta. So we write on x, the value of x, sorry. The value of x is eta. So we write down as eta into y raised to the power 1 upon beta to the power r into what is the value of x upon eta raised to the power beta minus 1. So this value is 1 minus 1 upon beta. And what is the value of this? E raised to the power minus y. So e raised to the power minus y and dx value is eta into 1 upon beta uh, y raised to the power 1 upon beta minus 1 into dy. So this we can write down as beta upon eta. So in this eta raised to the power r, we take outside from the integration from first term. Here we have eta upon beta, integration 0 to infinity. We have this y equal to r upon beta into y we have 1 minus 1 upon beta. Here we have y 1 upon beta minus 1 and e raised to the power minus y into dy. So when we simplify this, so beta to beta cancel, eta to eta cancel, So this can be written as eta raised to the power r 0 to infinity. So base is same, so we write down as plus 1 minus 1 upon beta plus 1 upon beta minus 1. This to this cancelled, this to this cancelled, and e raised to the power minus y into dy. So this can be written as eta raised to the power r 0 to infinity e raised to the power minus y into y raised to the power r upon beta into dy. So now here we use the definition of gamma function. So for using the definition of gamma function, so we write as gamma n is equal to integration 0 to infinity e raised to the power minus x raised to the power n minus 1 into dx. So here we have r upon beta. So this can be written as plus 1 and minus 1. So plus 1, so we take as this is a first term that is replaced by n and minus 1. So what is the value of this by using the beta function definition? So we write down using definition of gamma function definition. Sorry. So gamma function definition. So this gives us gamma n is r upon beta plus 1. So this is the moment genetic function. So moment genetic function of Weibull distribution. So mu r dash is equal to eta raised to the power r gamma r upon beta plus 1. So when you are going to solve the first movement, second movements, you can obtain. So when we put r is equal to 1, so this gives us mu1 dash. So this gives us eta gamma r equal to 1 means 1 upon beta plus 1. So this is the first movement that is also called the mean. So this is the mean. Similarly, you can obtain the second movement, third movement, etc. Now, when we are going to calculate second movement, that is mu2. So the second movement mu2 is equal to mu2 dash minus mu1 dash to the whole square. So you can obtain the mu2 dash also. So we can calculate the variance. Now we talk about the shapes. So when we talk about the shapes, so this is very important. If we have beta lie between 2 and 4. So when beta lie between 2 and 4, so this gives us normal shape. Gives us normal shape approximately. So if we talk about beta, which is equal to 1.25. So this 1.25 we are taking the value, so gives right skewed. Gives the right skewed. And when we take beta greater than 10, so this gives a left skewed. So gives left skewed curve. So these are the beta values. So on the basis of that, so we can draw the graphs. Suppose we are drawing the graph. So when we have approximately normal, so we consider as beta equal to 3. Second figure we consider as, so we having this type of graph. So here we have beta is equal to 1.25. Now when we, so left tail is longer than the right, so here we have beta is equal to 10. So these are the shapes we can show this. So now we take one problem based on the Weibull distribution. So parameters are given. If beta is equal to 2 and eta is equal to 5. So calculate the mean and variance. Calculate the mean and variance. So when we are going to calculate the mean and variance, so mean mean is equal to, we denote it as mu. Mu is equal to eta gamma 1 plus 1 upon beta. So we remember the formula. So we write down this as eta equal to 5 gamma 1 plus 1 upon 2. So this can be written as 5 gamma 1 plus 1 upon 2 means 3 by 2. So what is the value of 3 by 2? So we know the value of 3 by 2 is 1 by 2 into root pi. So 1 by 2 into root pi. So the value of mean 1 by 2 into root pi. So root pi you can simplify as 5 by 2 and root pi. Root pi value is, pi is value is 3.14 or 2 power 1 by 2. So you can simplify this. So this gives us approximately 4 point something, 4.43. So now when we calculate the variance, so for calculating the variance we denote it as sigma square. Sigma square is equal to eta square. So we have a gamma 1 plus 2 upon beta minus gamma 1 plus 1 upon beta to the whole square. So this is the formula of variance. This is the formula of variance. So eta square means 5 square is 25. 25. So this can be written 1 plus 2 upon 2 beta equal to 2. So minus gamma 1 plus 1 upon 2 to the square. So here we write down as 25 or 2 plus 2 is 1. So that means 1 plus 1 is 2. So gamma 2. Gamma 2 minus. So this gives us gamma 3 by 2 to the whole square. So this equal to 25. What is the value of gamma 2? Gamma 2 value is 1. Gamma 1 is 1. And gamma 3 is factorial 2. So we have the relation gamma n plus 1 is equal to factorial n. So now we write down the value of gamma 3 by 2. The value of gamma 3 by 2 is equal to 1 by 2 into root pi to the whole square. So this gives us 25 into 1 minus, this is 1 by 4 pi. So means pi by 4. So pi by 4. So this you can write down as 25 into 1 minus pi by 4. Pi value is 3.14 upon 4. So 3.14 upon 4. So this gives us approximately 5.375. So when we simplify this, so and you are going to calculate standard deviation. So this gives us root of variance. So root of variance, which is square root of 5.375. So this gives us 2.318.